part 2 of photoelectron spectroscopy. So in this photoelectron spectra, we have phosphorus and sulfur, and we're looking for two things. We want to have an explanation for why the 2p peak for sulfur is further to the left, so that would be more energy than that 2p peak for phosphorus, but the 3p peak for sulfur is further to the right, meaning it takes less energy. So phosphorus is element 15, sulfur is 16, so they have the same shielding, they're in the same period. Remember phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. If you think about orbital notation just for those three p's, you have one electron in each. For sulfur, exactly the same, except it's going to be 3p4. So if we look at that orbital notation, we have one pair of electrons and then two singles. So looking at our reasoning, we have sulfur has a greater effective nuclear charge than phosphorus. That is true. It has more protons. And the 3p sublevel in sulfur has a greater electron repulsions. That is definitely true. Let's see if there's a better answer. For part B, sulfur has a greater effective charge than phosphorus, still true, and the 3p sublevel is more heavily shielded in S than in P. That is not true. They both have the same shielding. For part C, S has a greater number of electrons than P. That's true. So the third energy level is further from the nucleus in S than in P. Not true. D, S has a greater number of electrons than P. So the Coulombic attraction between the electron cloud and the nucleus is greater in S than in P. It would not be because of greater number of electrons. So your best answer is A. Our next slide says look at the difference between sodium and potassium, and we're looking at the binding energy for the 3s. So potassium has 19 protons, and it is 1s2, 2s2, 2p6, 3s2, so the 3 s's are in there, 3p6, and then 4s1. Sodium, element number 11, 1s2, 2s2, 2p6, 3s1. All right, so why does it take so much more energy to take the 3s electrons from potassium? Your best answer is potassium has a greater nuclear charge than sodium. Part B says potassium has more electron repulsions. That would not account for greater energy. Sodium has one valence electron in the 3s. That's true, but it doesn't describe why potassium has higher energy required. Sodium has less electron shielding than potassium. They're both shielded. That is not the good reason for why potassium needs more energy to remove the 3s. So selection A is your best answer. Our next one says we have a photoelectron spectrum below, and which of the following best explains the relative positioning of the peaks on the horizontal axis? So we're looking at three elements here, and these three elements are oxygen, and then we have titanium, and then we have carbon. So we're looking at the relative positioning of the peaks. Why is oxygen there? And that is the 1s. It says oxygen has more valence electrons than titanium or carbon, so more energy is required to remove them. Part B, oxygen has more electron repulsions in the 2p sublevel than in titanium and carbon. Titanium would have more electron repulsion, so we can't choose this one. Titanium atoms are present in greater quantity than O, and that doesn't verify with our intensity. Titanium has a greater nuclear charge, but the 2p sublevel experiences greater shielding than the 1s sublevel. So your best answer is A for this photoelectron spectrum. All right, we're going to look at this spectra. So this is, let's just label it with the energy levels. So this is 1s, 2, and then, so 2 lines represents 2 electrons. So that's 2s2. Do note you have that little symbol. That means there's a great gap in your scale. And here we have 2, 4, 6. So there's your 2p6. Another big gap. And then we have 3s2, 3p6 it looks like. And then we got 2 little guys squished together. So this guy is the 4s2, the very last one, and the one next to it is the 3d1. So 4s electrons fill first and then the d's, but in relative energies, once the electrons are in there, the d's have, well, no, that just works like that. So I'm just going to stop my explanation. So if you look for your element, that is 3d1. Which element do you have? I have scandium. So let's see what we're supposed to do with this. Given the photoelectron spectrum of scandium below, which of the following best explains why scandium commonly makes a 3+ as opposed to a 2+ ion? So 3+, it would be losing that 3d1 and the 4s2. Part A says removing 3 electrons releases more energy than removing 2. Scandium's in group 3, and the atoms only lose the number of electrons that will result in a noble gas configuration. Part C, the amount of energy required to remove an electron from the 3D is close to that for the 4s, but significantly more energy is needed to remove the electrons from the 3p. There's the 3p right there. Removing 2 electrons alleviates the spin pairing repulsion in the 4s, so it's not as energetically favorable as emptying the 4s. Your best answer for this guy is C. Notice how close those energies are, so easy to lose 3 electrons. Our next one, we have magnesium below. So again, I think it's always best to write 1s2. There's your 2s2, there's your 2p6, and we have 3s1. Now, on top of that, we are supposed to draw the spectra for aluminum. So aluminum, oh, I just wrote the wrong thing for magnesium. It should be 3s2. Aluminum's going to have 3p1. So aluminum will also have 13 protons, so it's going to pull things a little bit tighter. So I'm going to do it in green. So that means it's going to take a little bit more energy for your aluminum. So my aluminum is going to be in green. It's going to take a little bit more energy to get rid of your 2s. So there's my 2s2, and I'm going to put my 2p6 in between it. The 3s2 would go a little bit here, be the same height, so make sure you do that properly. And then the 3p1, make it half as tall, and there's my 3p1. And so that's what I did in green. And here's the textbook, or I think this was a College Board question. So they have their 1s here, they have their 2s and their 2p, their 3s2, and their 3p1. Is it important that you have that less than the 2s for the magnesium? I think not. You just got to make sure it's less than the 2p for the magnesium. So there's your 3s2. Heights are important, and just shifting everything to the left. So we've looked at some different models. So we started with the Bohr model, where we just, not even the Bohr model, huh? How about the Dalton? You just have these spheres. Here's your Bohr model, where we have orbitals. And then we got to electron configurations and the Aufbau principle. And now we're able to look at photoelectron spectroscopy to see even more proof for our electron orbitals. So the data that we've used, Thomson figured out the electrons in the atom, Bohr used the orbitals, and from there we were able to get the bright line spectrum. Rutherford improved upon the Thomson model by going to the nuclear atom. And now we are using photoelectron spectroscopy to confirm our electron orbitals.